need to integrate by parts.
So if we don't get to integrate it, I like
It turns out you can. You know how we've been. You could. Did you know, this is an interesting but little known mathematical fact about power series. Instead of deriving Taylor series with derivatives, you can do so with integrals instead.
I bet he wouldn't have said that if you wouldn't have been right.
No, it wouldn't have crossed my mind. If you look up textbooks from like the 40s or earlier, the more common approach to generating power series was using integrals instead of derivatives. No, we're not going to do that. I always think about teaching it, but I haven't. Okay, so we have two ways we can generate a power series for that.
I think I like the integral of that more than I love it.
Well,
It's not just the power. It's
if
not just the power, it's a product.
right,
It's a product.
that's a product.
That would be in the ass.
It would be.
You'd have to use the chain rule, the product rule. Sorry.
It would be the derivative of the first.
It'd just be easy x and then
No, it wouldn't.
No.
No.
Yeah. So let's since we're on the subject.
You're not adding.
Yeah, f prime of x would be e to the x, because that's the e to the x's derivative, times the sine of x. Then the product rule says to multiply e to the x times the derivative of sine, which is cosine of x. Which you could choose to rewrite if you want by factoring out the e to the x's as e to the x times the sum of the sine and the cosine.
But it's okay. I can understand what you.
Okay. So here's what I need. Here's what I need you guys to do. I need you to find the first 4 non-zero terms of the power series here.
That's like what it is.
I know.
Non-zero term.
Yeah, well, sometimes terms zero out.
Especially in cosine and sine, like every other one.
So that means you may have to go higher than the third or fourth power to find 4 non-zero terms.
Wait, can we plug 0 in? Do you want us to do it center 0?
Yeah, we're going to center this at 0, correct. Yeah, McClear, you got paper? Okay, just checking.
I was having to remember
Hey, question. How else can I do this besides taking repeated derivatives?
repeated integrals.
Okay, besides me mentioning that weird fact, how else could I do it? Besides repeated integrals or repeated derivatives? The book mentions it, but I haven't talked about it in class yet.
I don't know the answer.
Okay, so no one's read the book?
I've actually gone through the book.
Okay, good. So an alternative, by the way, don't we know a series for e to the x?
Yes, we do.
Okay, we could write it down. And don't we know a series for the sine of x? We could write it down here, and then we could start distributing like the little distributing monsters we are.
That sounds horrible.
So here's what's going to happen. You guys are going to take repeated derivatives and try and find the first non-zero terms. I am going to attempt to multiply them together.
Yeah.
Okay? And then we'll compare notes and hope we match.
Yeah.
We better match. Okay, go for it. You're going to use Taylor's method. I'm going to multiply. Yeah, you might need to do a little algebra to clean those up, but there's really not much you can do. Warning. That's a good, I gotta remember that. That's a good one. We'll get in less trouble for that.
Yeah, with all your
Everything looks so weird.
Yes, you did. It looks like a giant mess.
No way, it's gonna be fun.
gonna get big and 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 big.
That's what I'm seeing too.
Keep working, don't cry.
I might not cry. It's just,
X squared, so that's x cubed. So
Second term, I got 4 terms.
I know, it just keeps growing and getting bigger.
Yeah, well, the next term I do is gonna have 8 in it. Actually, you know, at some point, these might start canceling out. This one just canceled this one.
Oh yeah, you're right. I'm seeing that.
x cubed.
Okay, so like. It's not positive or negative.
Whew. Getting there.
That's not logical. Does anyone else think that this is just growing
If I wanna
obnoxiously
take
large?
2 e to the x goes, that is 2 e to, it's just a constant.
It's just a constant.
What does that become? That becomes. Oh my gosh, what does that become? Okay, so that's.
We're still thinking here. If you're watching this, William, have fun. Good luck.
Sine x, like that. No, check it out. I went 4 terms down and I got a single 1.
Maybe I'll do that sometime. Soon. Wait, where? I got messed up. Where am I? What am I taking the derivative of?
There's another x to the 5th term.
Wait, where was I? Oh my goodness. How many terms are 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. And then you can say that the derivative sine is still a cosine.
Do we have a test next week?
Yep.
That is a great question. When is our test?
We're done covering chapter 10 today.
Wait, so it's Thursday?
No, I'll give you till next week. But I'm going to start new stuff on Thursday.
Our test next week.
So we We're going through 10-10, right?
You could take it Friday if, yeah, we're going to work on 10-10 today. Yeah. I mean, if you really want, Anna, you could take it this week.
But we don't have to.
No, you don't have to take it this week.
Okay.
So this would be x to the 4th over 24.
Oh my gosh, Courtney, there are so many different terms. Well, I haven't crossed stuff out yet.
Wait, I don't think I'm doing this right.
Thank God.
I think one of those is supposed to be positive, and I got them negative.
How did you get that one five? 'Cause that's what I was before for me.
1/20th.
So this turned into this. I crossed out these. This I could have just.
Is that sign right there?
Yes.
So that's your answer for sign. Because you just wrote it down there. You didn't take the derivative of this.
Oh, that's right. Sweep that
Can you
up.
please tell me what you got for 4
It's negative 4 e to the x sin x.
Negative 4 each of the x times minus 2.
You simplified it on the wrong one.
That's not what I
That's why I
got.
got confused.
I did it again, right?
See, that's why I got confused.
I did something wrong.
Okay, I got 4 non-zero terms. So here's what I think you should get for the coefficients. I'm just going to tell you to see if you're getting there. So the 0th term is 0.
Hey, that's what I got.
The first coefficient should be 1.
Got it.
Second coefficient should be 1.
Yeah.
Third coefficient should be 1/3.
I have 2. I got 2.
All right, we'll double check. Third coefficient should be 1/3. Fourth coefficient should be 0. And the fifth coefficient should be negative 1/30th, is what I calculated.
Oh wait, but that's with the 1 over n factorial.
You get to do divide by n factorial.
No, I haven't done that yet.
So you got a coefficient of 2. Divided by 2 factorial is 1. We match. We're doing good. Okay. We're getting there. Okay, keep working. I'm going to write down my derivatives next.
Well, you know, because it's like
What? No, you need to keep trying.
We got it right.
This is all about perseverance.
You're on the third thing.
and then after that, well, running a mile, you should get rid of
That's on the table.
Yeah,
So
so
there must
That's
be
how you do it.
another, oh, but that's good.
That's how you do it for everything, not just the problem.
yeah, that's why I was acting the Taylor series.
Oh, wait, no, I got that right too. Oh, okay, so I just haven't gotten that.
I'm just gonna go down to 10 and pick it up.
10.
I'm at 6. I think that's good enough.
Okay, it's just gonna
Well, I already got the first 3 constants and I've only gotten to 4.
Okay, well then I'll look for the 6 and we'll see.
Seriously though, this takes a lot of brain power.
Oops.
Oh wait, but then I crossed all those ones out. Jeff, can I see?
Careful on the numbers.
Okay.
Is that what you got for 5? Let's see what you got for 5.
Okay, so I see what I did incorrectly. I just don't understand. I got negative 3 EPS.
Oh. Shouldn't happen. So, oh, I said 3.
No, you got negative 4. I got 3. I got minus 10.
Right, I said you shouldn't
Oh,
have
this is
it.
not good. I get a 0.
Oh, yeah. Yeah, I know, you're right.
There's the first 4 derivatives.
Looks like you got 5.
I think I'm overcomplicating.
Oh yeah, that's right. I can't count. 5.
I'm kind of worried about
And
you.
you're
dude.
10.
Now I can't trust
And
you. I
chapter
don't know
10 is
anything
about counting. That was our first lesson.
Yeah, didn't we learn how to count?
Yeah. All right. So this right here, if I plug in 0, I get 0. If I plug in 0 here, I get 1. If I plug in 0 here, I get 2, but I have to divide by 2 factorial. If I plug in 0 here, I get 2 over 6 factorial, which is the 1/3 I was hoping for.
So I did it right until.
3 factorial, right, shit. Thank you.
Can't count today, Gary.
Yeah.
What's going on?
Well, 3 factorial equals 6, so I was thinking ahead. There we go. Okay. This one is 0. This one here is -4 over 5 factorial, which is -4 over 120, which is -1/30, which matches the other coefficient I have. Whew, I got it right. Well, I have 2 series that match. Hopefully they're both right. So exciting.
Wait. You need 4 in a row?
You need 4 non-zero terms.
Are you kidding me?
I got 4 non-zero terms.
So I've got 1, 2, 3, 4 there.
In a row?
No, 4 non-zero terms in general, right?
I was gonna say, I don't think that's
You are not guaranteed 4 non-zero terms in a row ever.
Okay, well, it's still not particularly popular.
Okay. So, how are we doing?
Good.
Okay, so I just want to show you the way I did it back here. Take a break for a sec. I know you're on a roll. So to pull off, you can multiply 2 infinite series. It just takes a while. Kind of. So the first line is 1 times everything in blue that I see up there.
Sounds horrible.
Shouldn't you have e to the x?
Yeah, this is e to the x right here, and this is sine of x in blue.
I'm gonna write that down.
Oh, but I have e written there. How do you get rid of e?
You have to write it as its power series like I did in black.
Oh, I do.
So I have 2 long power series that I need to multiply, unless you read the book, which you are required to do.
Are we?
Yes,
Are you sure?
yes. I say that all the time. Read the damn book.
He does say read the book also.
Is it?
Probably. We'll look it up after, Jeff.
Alright.
All right. The second line is x times the sine series, at least the first several terms written out. Notice how I staggered them so powers line up?
Yes.
Okay.
I do.
So just double check. I took 1 times all of these guys, and that gives me this row right there. Then I took, come on, pen, there you go, x times all these terms, and that is this row right there. And then I just kept doing that. I took x squared over 2 times the sine series, and I wrote that down next. X cubed over 6, wrote that down next. And then I started collecting terms. Now, I had originally stopped at this row right here, hoping that was enough. But then the 4th term ended up being 0, and I needed a 5th term, and I realized that I needed to go 1 more row to get the next 5th term. Because notice how they drop, x squared, x cubed, x to the 4th, x to the 5th. If I needed 1 more term, I would need another row.
So,
How do they get 0?
should we just,
So I've got negative x to the 4th over 3 factorial, and then I have positive x to the 4th over 6. They're the same thing, right? Except the SIG ends. Yeah, so I come down to add. So here I have 1 over 5 factorial, which is written here, 2 times 3 factorial, which is written here, and 24 is the denominator written there. So the coefficient of x to the 5th is going to be 1/20th minus 1/12th plus 1/24th, and my arithmetic tells me that's negative 1/30th.
so should we, like, assume to memorize sine, cosine, and e?
I'm going to list series that I wish you will memorize, yes.
Damn it.
I forgot to put 0 to e to the x.
Okay.
Supposed to be, in the second line, shouldn't it be x to the 4th over 4 factorial? Or x?
No, because I took, so this term right here,
Oh.
it's x times x cubed over 3 factorial. Yeah,
Got it.
so that raises the power. Yeah, so you have to be super careful here because it's easy to mess up the numbers. But it's not much more difficult than taking repeated derivatives.
Yeah, okay, I totally get it.
So if the two series converge, you can multiply them together to generate a new series. Now, if you do it that way, will you necessarily recognize a pattern to the coefficients? The answer is no. In any power series, are you guaranteed to find a pattern in the coefficients? The answer is no. But you usually have a process to keep getting the next one and the next one and the next one. So we do have a process. It's a pain in the ass, but it works. It is an option in some problems. I don't know. You know, if you're really good at multiplying and adding powers, this isn't so bad as long as you're careful. Alternatively, with the other method, you have to be really good at taking derivatives, right? So it depends on the day. Like today, I had a moderate amount of coffee, I had a cup of chamomile tea, I'm feeling pretty good. Both methods seem to work for me, right? Yeah, but if this were test day and I'm a little stressed out, I might decide that I can multiply and add powers easier than I can take derivatives. So I did it both ways because I wanted to see if the coefficients matched, just in case I screwed something up. So what if you don't feel like doing it both ways? What are you going to do to check this out? Okay, this is on a test. I'm not going to let you use, well, I'll give a take-home test where you can use Wolfram Alpha, but not on the in-class. So we're on the in-class test. What are we going to do to check this out? What are we going to do on the calculator? How do you do that on the calculator? Check to see.
Sequence thingy,
Yeah?
because
The sum sequence formula on the calculator means that you have to have a formula for the coefficients.
maybe we should make a formula.
Good luck.
Maybe.
I did not see a formula for this after staring at it for a while, okay? I didn't try that hard, but I didn't see it. So here's what I would do. I would graph the original function and graph my first few terms and see if they look close near the origin,
Oh, that's funny.
okay? So here's a graph of e to the x sine of x. Whoa, look at that thing. It's beautiful.
So what would the formula for this be?
Check that graph out. Okay. Now, this is interesting. When you multiply two sequences together, you have to see where their intervals of convergence overlap. Does anybody remember the interval of convergence for e to the x? All real numbers. Interval of convergence for the sine of x. Nope. Not -1 to 1. All real numbers. Remember, e to the x and the sine of x are very close relatives. They have the same interval of convergence. So this, although it does converge for all real numbers, we only have the first 4 terms. So that means our interval of convergence, our where it looks close, is not going to be very big. So we do need to look near the origin. So I should zoom back in near the origin. Okay, help me graph my terms here. The first one is x, right? Plus x squared plus x cubed over 3. You guys help me out here?
Yep.
Is that right? X cubed over 3. Plus, what's the fourth term?
-4/5 factorial
X to the 5th, right. There is no x to the 4th term. So then I'll have minus, that comes out to 1/30th times x raised to the 5th. Okay, ready? Check it out, look.
Okay.
Holy shit, that looks pretty good.
Pretty solid.
Ooh. Look at that. It hugs it for a little while here
Yeah.
before it diverges. So if we had another term, it would hug it better. Okay. So we did pretty good. It looks nice. It looks really nice on the integral from -1 to 1. Right? You can hardly see the difference in here. All right, so are we on the right track?
Yeah,
Yeah, we're on the right track.
I'd say so.
Is it easy to get the next term? No, but we could do it if we tried really hard. Okay. Would we be able to do any remainder testing on this? No. Not unless we know the next term.
And do we want to go find the next term?
We could find it if we wanted to.
No.
Okay, so we're going to do an easier one, so I'm going to back up a little bit. write down the power series. I would like the first two non-zero terms for the sine of x. Yeah, first two non-zero terms. Okay, so
Can I write more of that down?
what do you mean? Cut what I wrote here?
No, not that one, the other one.
This one? So I post all my notes in the doc sharing section.
Oh, okay, that one.
You-
That's what I meant.
You can get that out of the doc sharing.
Okay,
I'll
yeah.
post it there after class. Yeah, so remember, all my notes are in doc sharing. All right, sine of x. Oops. Oh, might as well make it pretty. What is the first term of the sine of x?
You already wrote it down, I know.
X, correct. Next non-zero term of the sine.
-3. Negative x cubed over 3 factorial.
Excellent. Okay, so I can say that the sine of x is approximately equal to that. Can't I? This is what we call T3, Taylor series, third degree,
Oh, yeah.
or Taylor polynomial of third degree. Let's make a note. Taylor polynomial of third degree, centered where?
0?
Yeah, centered at 0. You guys are just not willing to give that one up, are you? We're moving on to a new problem. I suggest you take a peek. You can play with that one later. I know it's fun and exciting. You just,
Just want to work it, man.
you want to get higher derivatives and more coefficients?
See if we can make formula or something.
Yeah, it's worth finding a formula. There is a pattern going on to those derivatives, right? Check it out. One term, two terms, one term, two terms. First power, second power, of coefficient of 1, coefficient of 2, coefficient of 4. What might the next coefficient be? 8, maybe? And then 16. Might it start doing some funky alternation in sign? We're going to need quite a few more terms to really nail that down. Okay, so feel free to play with that tonight if you can't sleep. In the meantime, let's take a look at this. This is a third degree Taylor polynomial centered at 0. It's approximately equal to the sine of x. So if we didn't have a calculator that would do the sine of x for us, like the sine of, like what is the sine of 0.1? How do you find that?
Really, really tiny.
Well, according to this formula, it is approximately 0.1 minus 0.1 cubed over 6. We can do that arithmetic.
Yes.
Let's do it. Let's do that arithmetic. So that's going to be 0.1 minus, what's that going to be? 0.001 over 6, right? 10 hundred thousands, which is really 1/10 minus 1 over 6,000. So if I just multiply this one by 600 over 600, then this is equal to 600 minus 1, which is 599 over 6,000. And should I do that division by hand? We can do it without. I did enough arithmetic. What is that approximately? It's not?
Yeah, that is.
You got to be in radian mode. And, yeah, in calculus, you should always be in radian mode. Never integram. Oh, yeah. Okay.
Yes, sir.
Okay, so it's pretty close, isn't it? Okay, so here's the question. On what interval can I use this to do approximations? Because at some point, it's not going to be so good. Like, what if I tried to use this to find the sine of 10? If I tried to use the sine of 10 here, yeah, I'll get, 10 minus 1,000 over 6. Do you think that's really anything close? Right? That's way, gosh darn off. I don't think so. Why did I bother plugging in 0.1? What if I didn't have a calculator with the sine button? How does the calculator figure out what the hell the sine of 0.1 is? How does it do it? How do? No. So what we have back here is that for some values of x, x minus x cubed over 6 gives us a pretty darn good approximation of the sine of x. For a certain, yeah. So here's the question: for what x's is this good enough? Oh, doesn't that mean I have to define good enough? Okay, let's define good enough. Let's say, let's see, earlier when I was playing around, I decided that good enough was going to be 5 times 10 to the negative 4th. So let's say good enough is 5 times 10 to the negative 4th. That is the largest error that I want to deal with. So I want no more error than that. Something like that. Jeez. All right. So how there's a formula for the Taylor series for dealing with error. So our error is our remainder. So I want the third remainder in absolute value to be no more than 5 times 10 to the negative 4th. And the remainder theorem says that that remainder is going to be less than or equal to some maximum value for that derivative, whatever derivative we're at, times the next term, call it n plus 1 over n plus 1 factorial. Okay, that's kind of the formula right there. What's the next formula? What's the next term for the sine? Oops. If we went one more term here, where would we be? Yeah, x to the 5th over 5 factorial. Now, tell me something about derivatives of sine. What are the derivatives of sine? They're sine or cosine, positive or negative, depending on where you stop. Okay, and what's the maximum value sine or cosine can achieve? 1. Yeah, so according to Taylor's theorem for remainders, then our maximum is going to be 1. So that means I want my next term, which is going to be the absolute value of x to the 5th over 5 factorial, in absolute value, to be less than 5 times 10 to the negative 4th. So what this will tell me is if I solve this, this will tell me for what x values this is close enough. And outside of that, I no longer have a close enough approximation. So I would like you to attempt to solve that red inequality. Okay, Anna? Do you need glasses or do you need to sit closer?
That arrow beneath the M.
Oh, that's supposed to be a 1, sorry. I'm replacing m with 1. Because the derivatives of the sine are always less than or equal to 1. Actually, what did I get on that? I wrote it down here somewhere. Oh, there it is. That reduces, I found that reduces to 3/50ths. Which should be like 0.6.
Oh, I got 0.06.
That's what I meant, 0.06, sorry, 0.06. Yeah. Yeah, so then I have to take the fifth root, so I'm going to get the absolute value of x has to be less than or equal to the fifth root of 0.06. Okay, what's the fifth root of 0.06?
5, 6, 9, 7. Sorry, 9, 6, 7, 9, 0, 5.
Okay, 0.5697.
6. I mean, wait, I'm sorry. It's the 7, 6, 7, not 7, 6.
6, 7,
9, 0, 5.
9. Okay, we'll stop right there. 0.569679.
Yes.
Okay, so absolute value of x has to be less than or equal to that. So as long as I pick x values that are smaller than 0.569679 and greater than negative 0.569679, then I'm okay. I'm within tolerance. What's tolerance here? Tolerance is 5 times 10 to the negative fourth. Now I claim I can even use these endpoints. Yeah, we will. However, I couldn't use the endpoints if I wrote the number this way. What if I wrote 0.57? What if I rounded to 2 decimal places? I would not be allowed to use the endpoints in that case. Why not? Because I rounded up. So whenever you're finding these intervals, the safe thing to do is round down. Always. So if you wanted only 2 decimal places, then the safe thing to do would be to say 0.56 if you only wanted 2 decimal places. Because otherwise, you jumped to the other side of this number and we're out of our interval of safety. What's it mean to be an interval of safety? It means that the end result is going to be within 5 times 10 to the negative fourth of the actual answer. So let's test it. Whip out a calculator. Yeah, it's called chopping or truncating. So yeah, if you wanted 4 decimal places, you would have to call it 0.5696. Yeah.
What?
Okay. Okay, focus. Come on. All right, so what am I doing? We are checking the endpoints. Okay, so points, tell me if I get this right. 5, 6, 9, 6. Hey, focus. All right, I'm going to take that number and I'm going to store it in x so I don't have to type it repeatedly. And then I'm just going to type x minus x cubed over 3. Oh shit, I hate when that happens. Over 3 factorial, right? Oh yeah, 3 factorial. Let's call it 6.
You need some parentheses, otherwise you're just going to divide that one by 6, aren't you?
Nope. Turns out it's okay. All right. So calculator says it's 0.5388, blah, blah, blah. Okay. Next, I'm going to calculate the sine of x for comparison. And I'm going to hope I'm in radian mode. I think I am. And I get 0.5393. Okay. Next thing I want to do is I want to subtract those two. So I want to take, which one's bigger? The second one. So I'm going to take the sine of x minus parentheses x minus x cubed over 6. Oops, I missed the over. And what's that? Yeah. And here I get 4 times 10 to the negative fourth. What do I want the error to be less than? 5 times 10. Did I achieve that? Yeah, I'm right at the end point and I'm just inside the margin of error. We're good.
Good job.
Pretty cool, huh? So we found that if we could afford a margin of error of 5 times 10 to the negative fourth. As long as we choose x values that are in this interval here, we are safe. At the very edge, we'll be very close to our margin of error. In the middle, we'll have many more decimal places of accuracy. Anna? This is finishing up 10.9, correct.
I was trying to do that homework, or like I attempted to start it, but
Yep.
I was too tired. We're probably gonna have a quiz over there.
We are going to have a quiz today, yes.
Really?
Yes, we're going to have another quiz.
Oh, do we get
Over
a
10.8.
quiz on the last?
Oh, I forgot about those. They're sitting on my desk. I will
I want to redo the first one because I understand it.
read what first?
I want to redo the first quiz because I understand it now.
Oh, okay, maybe. That's a good possibility. Yeah. All right, let's do another problem, and then we're going to do something different. Let's see. So do you think you get the whole idea of finding Taylor series now?
Yeah, just a little bit more.
Okay, good. I got another practice for you. Let's see. I have 2 different problems we can play with. You get to pick one. I know which one's my favorite, but you tell me. We could either let f of x equal e to the power sine of x, or we could let f of x equal the arc tangent of x. We're going to find one of those power series right now. I vote for the arc tangent, but you guys can vote too. I'm going to let class be a democracy today. We got 2 for arc tangent, 3 for arc tangent. Okay, might be a tie. What do you vote for, Zach? You said neither. You got to pick one.
I want to change my vote. I want to change my vote.
You got to vote for one.
Oh, what kind of democracy is this? You can always write it.
Okay, he's not voting. What do you? What would you like to vote for?
Sure, let's do the arts.
Okay, Anna, would you like to vote?
I'm not very good at art.
Okay, let's do arc tangent. So this one is in the homework. I'm pretty sure. So feel free to ask me about it if you see it in the homework and you get stuck on it. It's really not that bad. It's in 10.9 or 10.10. Okay, we're going to do the arctan. So strike this one for now. We may come back to it next class. We're going to do the arctangent. Okay, so we have a couple of ways we can do the arctangent. We can try and base it off another series we know, or we could take repeated derivatives of it. So let's see. Let's see if we can figure that out. Arctangent of x. Often the arctangent is written as the tan inverse of x, but I don't like that notation. I don't like the tan inverse notation. A lot of people take the reciprocal by mistake. And if you're going to enter this in some kind of computer algebra system like Wolfram Alpha or others, it prefers arctan. They take 1 over tangent as a common mistake. I'm sure you made this mistake once in your mathematical youth, Jeff.
I don't feel like taking over outside of X.
It's when it's outside,
Yeah.
Yeah. But there it's inverse function. Okay. So what's the derivative? Does anybody recall the derivative of the arctangent? 1 over 1 plus x squared. Yeah. U is great, yeah. Okay, excellent, good. Does this series look familiar, this black series there?
Wait, which black series?
Oh, sorry, there's 2 of them. Does this look familiar, this function? It turns out we found a series for that on the first day of Power Series. Yeah. It was related to the geometric series. So I'm just going to show you 2 different ways to do this. This is a review of section 7 also. We first found a series for 1 minus x, which is 1 plus x squared plus x cubed. It's a geometric series, right? Plus x to the 4th, blah, blah, blah. Geometric series. That's our first power series, right? Should be proud of that one. It's like your first pair of shoes or your first big boy underpants. It's your first power series ever. Do you see how we could do a couple of substitutions here, or one substitution, to get a series for this guy here. If I replace x with negative x squared, I will have this. And if I put a negative x squared in place of each of these guys, I will have a series. Way too quiet. So I'm going to do that. Let's see, I need to shuffle this down a little out of my way. Can I catch it? I think I caught it. Okay, so my belief is that this function right here has the following series. So this guy is equal to 1 minus x squared plus x to the 4th, because the square will cancel the negative, minus what? X to the 6th. X to the 6th plus x to the 8th. Do you see a pattern? Minus x to the 10th. Right? So I replaced x with negative x squared. Okay, so that is a series for 1 over 1 plus x squared. How can I turn this red thing into a series for the arctangent? How do I go backwards here?
I have a question.
What?
Obviously, we've got a.
Yes.
Obviously, I probably didn't.
Okay.
1 over 1 minus x. How does that give us that series?
Geometric series?
Yeah.
Do you remember the formula for geometric series? It's the first term divided by 1 minus the constant multiple. What's our constant multiple to get next term? X.
Oh.
So it's 1 over 1 minus x. See it now?
I see how you mean it. Yeah.
Courtney?
Sort of.
Okay, so I'll rewrite it this way. Is this a geometric series? And the formula for the convergent geometric series is the first term, which is 1 over 1 minus the common factor. So replace r with x. That's it. Yeah. Okay. So how can I turn the red series into a series for the arctangent? I have to reverse what I did right here. Take the integral, right? We took a derivative to get here. We have to take an integral to get back. So let me write this down. So we know that 1 over 1 plus x squared has the following series. 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, yada, yada, yada. And if we integrate with respect to x, then I should then get a series for the arctan. Oops. Because the integral of 1 over x squared is, 1 over 1 plus x squared is the arctangent. Now, when we integrate, we get a positive constant, right? If there's no boundaries, so this is going to be c and then plus. What's the integral of 1? Minus the integral of x squared. X cubed over 3, or 1/3 x cubed, either way. Integral of x to the 4th. Excellent, 1/5 x to the 5th. Minus x to the 7th over 7. La la la. We did it. That wasn't that bad. Now, what's the alternative of, oh, we got to figure out what c is. Ah. Okay, let's see. To figure out c, we need to know the interval of convergence. That would be the interval, the first interval that the arc, oh no, that's the only interval the arctangent lives in, right? Well, no. Actually, the arctangent is defined for all real numbers. But the y values are bound between negative pi over 2 and pi over 2. The tangent's the other way around. Okay, so let's see. What is the interval of convergence for a geometric series? Nope.
-1.
Yeah, this only converges if the absolute value of r is less than 1. So that r has to be between 1 and -1. So that interval persists through our screwing around. Substitutions are a little dangerous. We replaced r with a negative x squared, so that gives us negative x squared. Has to be between 1 and -1. Oops, why did I put equals 2 there? And then I can solve that for x. So if I multiply by -1, that switches everything. So that's going to give me 1 is greater than x squared is greater than -1, which I can rewrite as -1 is less than x squared, which is less than 1. Then I take the square root. Now I can't take the square root of this side, so that's out, because that would be imaginary numbers. So that implies that the absolute value of x, because the square root of a square is the absolute value, has to be less than 1. And so that takes me back where I started. But I had to check to be sure. Okay? It wasn't obvious. All right, so what that means is for this particular series here, I know that an absolute value x has to be less than 1 to have convergence. Do I know what happens at the endpoints? No, the endpoints can always change when you do a substitution or when you integrate or differentiate a series. So we have to check x equals -1 and x equals 1. You guys check them. Tell me what you find. Does it converge or diverge at each endpoint? Now, are the endpoints usually independent of each other in terms of their convergence or divergence? Yes, they are. One could converge, the other could diverge. They could both converge, they could both diverge. We never know what happens until we try. Give it a shot. What do you think, Mr. Intuition? Convergence and divergence when I plug in -1 or 1? Does the series converge if x equals -1? Does the series converge if x equals 1? Do I have convergence at endpoints? Oops.
I believe so.
It looks like it. I know how to do it.
So that's what I get if I plug in -1, I get this alternating series. Is that right? C is some constant. I don't really care what it is right now. So I can just cover up C. That's an alternating series. Okay? Does it strictly alternate? Are the terms ignoring the signs decreasing? And do the terms go to 0? So it's convergent by the alternating series test. Okay, so we have AST convergence. Oops. What about on the other side? On the other side, I'm going to get C plus 1 minus 1/3. It just changes the alternations. Minus 1/5 plus 1/7. So this is the opposite of what I found there, which must also converge. I don't know. Plus, minus, there we go. So this is also convergent by the alternating series test. All right, so it converges at both intervals. So what I have as far as an interval of convergence is -1 to 1. Both endpoints are good. It's kind of cool. I don't think that's happened to many of the ones we've done before where it converged at both endpoints. All right, let's find C now. What's a convenient number to plug in for X to figure out what the hell C is? 0 is a wonderful number to plug in. Okay, what is the arctangent of 0?
0.
It is 0. What happens if I plug in 0 over here? What do I get on the other side?
Wait, what?
What happens if I plug in 0 on the right?
C plus 0.
I get C plus 0, so C must be
0.
excellent. Now we know a series for the arctangent. So the arctangent of X is equal to X minus X cubed over 3 plus, oh my gosh, check this out. Oh, this is awesome. Wait till you see this. This just made my day.
Oh.
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 If I were to let X equal 1, which I did a minute ago, then the series I get is 1 minus 1/3 plus 1/5 minus 1/7. We attempted this series in class one day a week or so ago. And what we established is that this was a convergent series. But we did not know to what number it converged.
We're gonna find out.
Yes, it converges to the arctangent of 1. Okay, let's see. What is the arctangent of 1? That means the answer is the tangent of some number equals 1. When does the tangent have a slope of 1?
5/4.
Pi over 4. Holy crap. The sum, the alternating sum, oh shit, wrong number. I got all excited there. Who's ding? Was that me dinging or that was me dinging? Sorry, I gotta turn that off. I think somebody dinged. The sum, the alternating sum of the reciprocals of the odd numbers is pi over 4. Did you hear that?
Yes.
The reciprocals of the odd numbers, if we add them up, alternating, we get pi over 4.
That's cool. I mean, I like that. I don't know why.
Like, how do people find pi? One way you could find pi is taking 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. And if you want more decimal places, add more terms. That's one way to find pi. It's a slow way to find pi, but it works. Let's check it. Some sequence on the calculator.
Are we checking whether it equals pi or whether
We're checking if we take 4 times this series, we get pi, pretty close to pi. So we're going to do a sum sequence on that sucker. You guys use the calculators. I'm going to use GeoGebra. Okay, so let's see. Blow this sucker up. Font size 24. Sum sequence. Expression is 4 times -1 raised to the power n divided by, let's see, I'm going to start n at 0, so I'm going to go 2n plus 1. Variable is n, starting at 0, ending at, I'm going to do the first 100 terms. Calculator says 3.15. Darn, it's slow. 5 decimal places, yeah. We're doing the sum of the reciprocals of the odd numbers, alternating. We're entering this, right? So there's a couple of ways to do it. If you start n at 1, then you're going to want to have -1 to the n minus 1 over 2n minus 1 times 4. So that's one way to do this series. I started with n equals 0, so mine looks slightly different. I started with n equals 0, so mine looks like this. Sum, let's call it k, goes from 0 to infinity of 4 times -1 to the k over 2k plus 1. I didn't want to type n minus 1 as the power. That's why I did it that way. Kind of lazy. Okay, so after 100 decimal places, I only have like one decimal place of accuracy. 3.15. So maybe I could do 1,000 terms. I don't know if the calculator can do 1,000. Maybe. Oh, 3.14. I have 2 decimal places of accuracy. Guess what if I go out 10,000 terms? 3 decimal places of accuracy. Yeah, converge is wicked slow. It's painfully slow. So I'm going to go out 10,000 terms. 3.1415. I got 3.1416. Okay. So it's a slowly converging way to get pi. I went 10,000 terms and that's what I got.
Oh, okay, well, I got negative number.
Okay, so did you get the negative pi though? That means you have your alternations in the wrong spot.
Negative 3.1315.
Yeah, so that means you have your, so if you look at, you have your negative wrong. So if you have an n here instead of an n minus 1,
-1.
yeah,
That's okay.
so you have the opposite of what we want. You have the left-hand endpoint instead of the right-hand endpoint. Yeah, so you got to be careful and double check that your signs fall in the right spot. That was exciting, wasn't it? I thought it was pretty exciting. I wish it converged faster, but hey, it converges. No, they have much more sophisticated routines that converge much faster. Yeah, so here, if I wanted the billionth decimal place of pi, I would need 10 to the billionth places in this term, which is just ridiculous. Yeah, this is way too slowly convergent, but it's a start, right? Okay, so series that should be familiar. Let's take a break, and then I'll do that. So take a potty break. I'm going to start a new broadcast.